Equations can arrive in many different situations in algebra and studying functions. For example, we had our earlier example of a person throwing up a ball in the air. And then we want to find out, for example, when the ball hits the ground. So let's say here that the height over the ground as a function of time x, or if we want to keep more, we have letters the same as we are investigating. So h for height and t for time. So let's say he throws it up from 2 meters, starting height of 2 meters, starting velocity of 10 meters per second, and then it accelerates towards the ground due to gravity. So then it's given by this formula. And then we want to ask when does it hit the ground? That is, when is the height 0? So when does it hit the ground? When is the height 0? Then we have an equation to solve. Then we want this to be equal to 0. So to find out when the ball hits the ground, we need to solve this equation, meaning that we want to find a time t that makes this true. You say it solves the equation. We want to find a time that solves the equation. Okay, so that's what we're going to study now. Let us start with a little bit simpler equation. For example, 3x plus 2 equals 8. So here we are looking for a number x, an unknown number that will make this true. Okay, in this case it's not hard to guess what it is or see quickly. If you just try some numbers, you'll find out that 2 works. So 2 is a solution. But then of course you could also ask, are there more solutions than 2? In this case also it's not hard to convince yourself that no more solutions than 2. But we are not after solving this equation. We are after a method for solving equations. So when we start with an equation like this, let's interpret it in terms of weights. So let's say we have a balancing weight here. So we have an unknown weight of x. So 3 identical unknown weights of the weighing x. And then we also have a weight of 2. And this balances on the other side 8 kilograms or whatever unit we're using. To be fair, actually if we do physics correctly, all of these weights should be at the same place and the same distance from here, but we are after just the principal point here. So we think that these are in balance, so it's the same weight on both sides. So what we want to do is to find this unknown weight that makes this balance. So how can we do that? We could, for example, take away 2 kilograms on both sides. Since let's assume now that this x is a weight that balances this. If we had found such a weight, then if we take away 2 kilograms from both sides, then we'll still balance the weight after we have done that. So if you take away 2 kilos on both sides, so if it balances this, then after taking away 2 on both sides, you still will balance the scale here. Okay, so if we have found a solution to this one, we have found an unknown x that balances this, it will also balance this. So if we know that it balances this, it must balance this. And also oppositely, if we know we have found a weight that balances this, then you can add to both sides 2 kilograms, and then we know it will balance this. So these are equivalent, these two situations. We know if we have found a solution to this one, with solution we mean weight x that balances it. Then if we have found a solution to that, then we have at the same time found a solution to that. And oppositely, if we have found a solution to that, we have also found a solution to that. So we say that these two situations are equivalent. So these two situations are equivalent, meaning that if one is a solution, if we have a solution to one, we have a solution to the other. And also if it's not the solution to that one, is neither a solution to this one, and oppositely. So they have the same solutions, these two. And this here we can write as an equation also. Here is 3x equal to 6. So these two equations are equivalent, and that we write with the double pointing arrow. And that means that these two equations have the same solutions. So instead of solving that one, we can just as well solve this one, because they have the same equations. And this is a little bit easier to solve than this perhaps. And we can continue in this fashion. We could translate them to equivalent equations. And then finally we hope to end up with an equation that is very simple to solve. So we could continue here now. If we have this situation, then we can find another situation. Let's say we have an x that balances this. If we take away a third from this side, how much do we have then? Then we have x left. So you take away a third from that one. And take away a third from the other side also, then we have 2 there. So we see that if we have found a solution to that one, then it also will be a solution to that one. And oppositely also holds. If we have found a solution to that one, then we can add 3 unknown there and 3 2's there. And then we get this situation, and that will also balance that. So these are also equivalent. Meaning that this equation is equivalent to this equation. And this equation is very simple. Maybe it hardly looks like an equation, but it is. It is an equation. When you put 2 here, it's true. And if you put something else than 2, it's not true. So this is an equation, a very simple equation. And this is obvious how you should solve this one. You see that the only solution to this one is 2. And that means that since all these 3 are equivalent, that means that if you have found solution 2 to that, that must be the only solution to that and to that. So they have the same solutions. Meaning that we know now that the only solution to this one is x equal to 2. And that we saw earlier that 3 times 2 is 6 plus 2 is 8. So this is the method for solving equations. You take an equation and you transform it to an equivalent equation. Not the same, but an equivalent. Meaning that they have the same solutions. And by doing this stepwise, you end up, hopefully, in the end with an equation that is so simple you see the solutions directly. And then you have solved all the original equation also. So you have found the solutions to that. So that is the method we want to use. So what allows us to make equivalent equations? Yeah, we could, for example, if we add same thing on both sides, we will have a new equivalent equation. If we subtract the same thing on both sides, we'll also have an equivalent equation. We could multiply on both sides. However, we can't multiply by 0. But that doesn't make an equivalent equation. So let's see an example of that. Okay, so let's say here we have x plus 1 equals to 2. It's obvious what the only solution to this one is x equal to 1, of course. But let's say now that we multiply both sides with a number. Let's say we multiply both sides with 0. What do we get then? Okay, here we have a new equation. You can also write it as simplified as this. What solutions do this equation have? Or that one for that matter. It has infinitely many solutions. Any x are a solution to this one. Because no matter what we put for x, this will be true. 0 times whatever is still 0. So this equation has solutions are equal to all the real numbers, infinite and many solutions. However, this only solution to this was 1. So we see if we multiply by 0 on both sides of an equation, we don't have an equivalent anymore because here are not the same solutions. So you can multiply an equation on both sides with a number, but not 0, because then you don't have an equivalent equation anymore. You can also divide an equation on both sides. So you divide the same number on both sides, you also have an equivalent equation. But you can't divide with 0. And that's obvious because you cannot, it is undefined to divide by 0. So you can't do that. So we see here, to make equivalent equations, we can add any number. We can subtract any number. We can multiply and divide with any number, but not equal to 0. So we can multiply both sides, but not equal to 0. It's important now to remember that if you add or subtract or multiply both sides, it must be the same number on both sides. So we can't multiply one side with 5 and another with 7, because then we don't get an equivalent equation. It must be the same number on both sides we add, subtract, multiply, or divide. But so long as we stick to these here, we are making equivalent equations. An important point here is that, should keep in mind, is that this here, for example, is a mathematical expression. So this is a mathematical expression. And this is not an equation. It's just a mathematical expression. And if I put 1 here, this is a mathematical expression. If I connect these two mathematical expressions with an equal sign, then I will make an equation. So if I have two mathematical expressions connected with an equality sign, then I have an equation. So if I have an equation like this, if I have a mathematical expression like this, I can't just start to multiply it with a number. For example, if I multiply by 5 or 6. So let's say I want to multiply by 6 because I want to get rid of the denominators. But if I do like this, I have created a completely new mathematical expression. So I can't just, if I have a mathematical expression, just multiply by 6 and hope that everything will stay the same. However, if I instead have a mathematical equation, for example, this one, then I can multiply with the number on both sides, excluding 0. So if I do like this, then these two are equivalent. They are not the same equation. So if I multiply with 6 on both sides, I create a new situation where it's 6 times larger on the left hand side, 6 times larger on the right hand side. So I created a new equation, but I have created an equivalent equation, meaning that they have the same solutions. So it's not the same equations, but the same solutions. So when I solve equations, I can change, because it's not so important that the expression is the same. The important thing is that they are equivalent. However, when I work with mathematical expressions, the important thing is that they are the same. So if I, for example, start with this one, I can't just suddenly write this equal to this, because then I can't put this one here, because they are not equal. So when I'm working with mathematical expressions, I'm interested in equality. When I'm working with equations, I'm interested in equivalence.